It's my immense pleasure to introduce today's keynote speaker, Dr. Martin Otto, Head of Cybersecurity Research Group at Siemens Technologies. He's currently Head of the Cybersecurity Service Innovation at Siemens Corporation in Princeton, New Jersey, in USA. His mission is to provide Siemens business units with technology solutions and innovations that enable Siemens to provide state-of-the-art security services to customers. A particular focus is on helping Siemens customers that operate energy systems and other parts of the national critical infrastructure to detect, to react, and to mitigate and otherwise defend against cyber attacks. Dr. Martin Otto is a researcher and research manager with Siemens Technologies R&D organization since 2005. He held positions in the US, Canada, and Germany, among them as global head of the Siemens CERT. Before that, he got a PhD in computer science in 2005 from Paderborn University, Paderborn in Germany, working on fault attack side channels on smart cards, a topic that got him hooked on the field of IT and cybersecurity, a field that has not lost its fascination ever since for him. I just want to make one more comment. Siemens Technology graciously contributed the hardware for embedded security challenge, and Martin will also be judging, besides side by side one of his colleagues, ESC on Friday for US, Canada, and MENA regions. And before I hand off to Dr. Martin Otto, if you have any questions, use the Q&A button to add in your comments. On that note, welcome, Martin.
Yes, thank you very much, Rajesh, for the nice introduction. And of course, for having me here today. And also warm welcome from my side to everyone who's joined globally from all over the world. So that's really great to see the number of competitions you have and the engagement that you have. So that's really great. So I hope you see my slide. If not, I'm sure someone will tell me. I basically want to take your mind off a little bit from the competitions and take you on a journey into the area of industrial cybersecurity services, and specifically in the area of utilities. And of course, you may ask yourself, why should you listen to me on that? So a little bit background on me and Siemens, the company that I represent, so you kind of know who we are if you don't already. So Siemens is a pretty large company. We have about 360,000 employees and probably in 200 countries. So wherever you currently are in the world, there's probably Siemens somewhere. And we're focusing on a lot of industrial areas. So here on the slide, you see a simplified version. We're mostly looking in digital industries. So we're manufacturing plants or control systems for manufacturing plants. We're in smart infrastructure, which is building automation and smart grid, digital grid topics. We're in mobilities, we build trains and equipment to run train systems. Siemens Advanced is our consulting arm. We have a lot of smaller companies, and I will spare you the details of that. And then we have Siemens Healthineers, where we produce MRI, CRT devices, ultrasounds, and stuff like that. So a lot of these topics are in areas which make up nation's critical infrastructure. So that's basically the background I'm coming from. And then within Siemens, and I mentioned that already, there's this little department called Siemens Technology, and the handsome guy here on that slide, that's me. Pre-COVID, a lot more gray hair today. And I'm part of Siemens Central R&D organization. So it's basically our CTO organization, and our job is to prepare topics for our business units, to come up with new innovations, new inventions, technology scouting, and in the end, help our business units to stay in business. So enough about me. Let's talk about content. And as you can imagine, no self-respecting presentation about cybersecurity can do without this, oh my God, everything is getting worse kind of slide. So this is mine. There's a couple of things that I wanted to point out. So what you see here is basically an evolution of attacks on the lower end, and basically an evolution of industrial automation with the blue arrows. And it's not surprisingly that decades ago, the focus of attacks was mostly on the IT side, but we've seen that with increased connectivity of industrial environments, be it like pure manufacturing or energy. The attacks just left the pure realm of IT and have affected more the OT side of things. And there have been a lot of notable ones, from Stuxnet, basically the first notable attack that bridged air gaps to the attacks that were made possible by the introduction of IoT devices like the Mirai attack. We've seen more targeted attacks specifically on industrial environments, like the Indestroyer attacks on Ukraine, or more recently, the attacks on Colonial Pipeline and Oldsmar in Florida, the water treatment plant. We've seen a lot of ransomware that no longer just hits IT equipment, but OT equipment as well, like again, Colonial Pipeline. And the latest threat or the latest trend that the bad guys have figured out is to just do supply chain attacks, and realizing that maybe I don't have to attack my target directly if they are nice enough to install compromised software or commission compromised devices. And most notably, these were like the SolarWinds and CSAW' ransomware attacks. And all of these attack and affect industrial environments more and more. And so it becomes a significant threat and a significant risk, especially if a lot depends on these industrial environments. And this has been probably recognized, of course, and it's not news for you that of course this, or the severity of the risk and the potential attacks is I think well understood these days. And there's this famous quote here by Ian West, head of cybersecurity at NATO, who said that an individual equipped with a laptop can bring about greater destruction than a conventional weapon. And of course, that is due because of the widespread connectivity and the fact that now you can basically sit anywhere in the world and launch attacks that potentially have devastating impact. And from my perspective, and that's basically my quote on that, is there's a huge difference between whether we look at traditional IT systems or industrial environments. And I always like to put it in this way: if you mess up IT security, you might not get access to Facebook for a day. And you all know how important Facebook is in everyday's life. But typically, if we lose availability in IT, that is something we know how to deal with, and something we can live with and recover from pretty quickly. And of course, there are exceptions to that rule, but in general, right? In cybersecurity, however, if you mess up in cybersecurity, the whole East Coast goes dark. And sorry for those who are not in the US, I'm sure you have your own geographic region that you can plug in here. But the core message that I want to send is like, if you imagine the potential damage that can happen if you attack industrial environments, then it goes way beyond convenience, or way beyond basically just being able to see what your friends are doing. But it can cost lives, right? Especially in energy, if the lights go out. And of course, this is a pun on the famous 2003 widespread blackout here on the East Coast in the US. If hospitals lose power, if people get stuck in elevators, if process or chemical plants lose power and maybe control over their reactions, if air traffic control towers lose power, if train systems lose power, of course, all of them have a limited backup capability, but at some point in time, this can really cost life. So typically the stakes are a lot higher in cybersecurity, or industrial cybersecurity. And so I hope to get you excited today a little bit about this topic, and hope to maybe influence your research direction or your future career a little bit in that direction, because I believe it's a fascinating topic, and there's a lot of work to be done, and it's really a career worthwhile pursuing. So since I don't know the background of everyone, I thought it's probably a good idea to explain in a little bit more detail what's really the difference that we have here between IT and industrial security. Typically, industrial security, we also call it OT security for operational security, so IT versus OT. I'm sure most of you have heard about that. The main difference I try to capture it on this slide, right? But the main difference between in IT security is that confidentiality is king. So typically, whenever you look at the three dimensions, confidentiality, integrity, and availability, in IT, confidentiality is really the one with the highest priority. Protecting personal identifier information, passwords, credentials, health information, all of these things typically have the highest priority, in general, at least in IT security. In industrial security, it's very different. Here, availability is key. And that's not to say that confidentiality and integrity is not important, but typically availability is significantly of higher importance than the other two. Like, as I said before, if the light goes out, then the problems go way beyond just the realm of your utility and the individual company and can have devastating effects. There are also a lot of smaller aspects where the differences are telling, and 5 of them I decided to present here. So one is about asset lifecycle. So in IT, you're typically used to the fact that you replace your laptops, your phones every like 3 to 5 years. In OT security, as it's not uncommon to find assets in the field that are there for decades, 20, 40 years, some longer. And you can imagine how they look like, and because you have an idea how the internet looked like 20 to 40 years ago. The same is to the software lifecycle. In IT, you typically have forced migration. So you've probably all had that experience, like that after a couple of years and a couple of new versions, you either upgrade your phone or your laptop, or it basically becomes unusable. So you have this forced migration and you have this forced renewal of systems. That is very different in industrial security, because here equipment is typically used as long as spare parts are available, and that is decades. Then as cybersecurity experts, right, as defenders, what are the options for us to protect these devices and add additional security functionality after the fact if we have devices in the field and we find that we have to deal with new attacks and new threats? In IT, our options are really high, right? In a typical business PC, you have more than 10 agents that realize various security-related functionality to protect the environment, the user, and the system. And that's your typical antivirus or host-based intrusion detection, but also asset inventory, e-discovery, and a lot of other things. That's not an option in OT. Typically, most of these systems are pretty much maxed out in terms of bandwidth and capability. So there isn't really a lot of possibility to add additional agents or additional software if these systems, enable such a concept to start with. Same is true in heterogeneity, right? In just looking at Windows, in IT, you typically find 2 generations. So it's probably Windows 10 and 11 now. I hope no one's stuck on Windows 7 anymore. And in OT, it's very different. If you go in industrial and energy environments, it's really not uncommon that you find devices from all over the history of operating systems. So Windows 95 and up is still there and still in operation. And of course, the same is true for other operating systems, Linux, Unix, as well as custom operating systems. And that also influences the main protection concept. Right? In IT, we're pretty advanced. We have standards. It's for the most things, it's pretty well understood what you need to do to protect systems. I'm not saying we're still studying with topics there, but we kind of have an idea with what to do with patching and agents and how to harden systems and how to manage it. So you have standards that you can audit against. It's fairly well understood. In OT, we're not there yet. So in reality, a lot of the utilities, a lot of the manufacturing environments still do like a custom approach to security. So it's a case-by-case basis and a risk-based approach, which means it's a lot more error-prone than what we're seeing in IT security. And so the question is, well, it's different, okay, but we seem to have come a long way in IT security, right? It looks like we have this to some degree under control, and we still see new attacks, we still see ransomware, we still haven't solved all our problems, but there's a lot of knowledge, a lot of expertise already available. Can we just take it over to OT as well? And then we have a lot of research going on, right? And I really liked what Steph said before about the competition for the applied research. There's a lot of great work being done on your end in academia, right? From professors, from students, PhD, master students, whatever. There's a lot of great ideas coming out of that. And we need to figure out basically why don't we just, or how can we just apply them to products and bring them in the field? And you may be aware of that, but typically a lot of these ideas meet what we refer to as a valley of death. So there's a lot of great ideas coming either from IT or coming out of research, and they provide you have great papers where you show that concepts can work, and we would like to make it usable, right? And then we look at product development and we try to commercialize these products, these ideas, but we see that a lot of ideas basically don't make it. And it's probably no brainer, but it turns out that many ideas don't make it because commercialization turns out to be much more complicated in practice than envisioned. That there's a lot of things that you need to do other than just implement your idea, right? You need to You need to properly test it. It needs to comply to standards. And from our perspective, coming from corporate research, is that also the revenue potential needs to be convincing, right? So that's why we like to work with academia, and that's why I like these kind of competition and these kind of ideas coming up, because we're looking for the right ideas that are not just good, but are also so good that this valley of death can be basically crossed and survived, and we figure out how we commercialize these ideas, put them into products, and increase the security of, in this case, for example, the utilities. But let's get a little bit more into the weeds, right, and look at the challenges, as I promised in the beginning, that utilities face, specifically in running and operating their environment in a secure way. And specifically, of course, I'm focusing on the digitalized 21st century energy grid. So what you see here is like a typical circuit breaker, but these systems are not, air gapped anymore, right? They're not just standing there and doing their job on a purely physical layer. So all these orange cables that you see, most of them are probably communication connections. So these devices are all networked these days, and for a good reason. And that reason is digitalization. So it's a new hype topic, but it has a lot of value behind it and a lot of reason behind it. And in the end, it all boils down to that famous quote that's attributed to Clive Humby in 2006, and working for the UK supermarket chain Tesco, who coined the term of data as the new oil. And it is true that we found out that if you have access to data, to log files, if you know what's going on and you can analyze it and you can interpret it, that you can generate a lot more value. You can do a lot more things than just with the physics alone. And in the area of energy and utilities, it means you can enact much more granular control. So that means you can prevent more blackouts, you can be much more efficient, you can prevent a lot of things that typically cost money or cost loss. And so there's real value in getting this data and in getting the value out of this data. However, it comes at a price, right? And the price is increased connectivity. And increased connectivity means that, well, whenever you have connectivity, you have potential entry points into your networks. Well, and we're all cybersecurity experts, right? We know what that means. Increase attack surface, so potential to do more attacks. So what are the challenges then for a utility? Well, first, if they want to build their digitalized 21st century energy grid, first they actually need to build it, and then they need to operate it. And the security task here, and of course I'm simplifying, which is the benefits I have in doing a keynote. In building, it's mostly these three things, right? You need to design your network, and then you need to figure out where do you find the right equipment that can be configured in a secure way. And it sounds pretty straightforward, but it means that the utility has to have enough experts who understand what security configurations they need for their specific environments. What features do the products need to have? And are the features that the products offer really good enough so that they offer the kind of configuration that you need to build your network securely? And the next challenge is to actually configure it securely. So once again, you need to have the right experts on site in your company to understand how to do that and how to make sure that all these different devices that you need and plug together, that all together, the configuration is really secure. And that, so far, is just addressing your own sense of security. Now, of course, typically everything in critical infrastructure is heavily regulated. And for North America and utilities, the important standard here is NERC-CIP, and it stands for North American Electric Reliability Council Critical Infrastructure Protection. And while I will not quiz you on that, we will actually see that standard coming up in a later slide again. And in the end, it's a good thing that critical infrastructure is heavily regulated, because that basically what reduces the risk and what keeps the lights on longer. But it also means that now utilities have to figure out that whatever they build strictly complies to these requirements. Now, once they've done all of that and they plug it in and they switch it on, and 1 second later it's in operation and it gets attacked. So now the challenges are to ensure secure operations. And this mostly boils down to three topics. One is continuous transparency, which you typically achieve via continuous testing. Now, vulnerability scanning, penetration testing, auditing. You need to figure out if after a while your system is still in the secure state that you think it is, or if there are vulnerabilities that you are otherwise not aware of. Then you need to adapt to maintain a secure state. So mostly that boils down to patching, but you may also need to update configurations. You may need to update devices that go end of life, even in these environments with decades of lifetime. And you need to figure out basically how to update your entire system so that the resulting configuration has the same security level as before. And the last topic is monitoring and attack detection. Monitoring and attack detection. And so here you need to collect data, and you need to figure out where in that data can I find evidence of attacks so that I can act on it and contain it and respond to it. And I'm going to go into these three topics a little bit deeper to show a little bit more what the practical challenges are that we meet when we try to help our customers. So first, continuous transparency via testing. So this is basically my picture of most of you guys as students today, and then in the future operators in industrial or energy environments. And of course, you're used to having devices like the phones shown on the picture. So you're basically used to having the entire internet at your fingertip, right? You're used to a certain level of usability and user experience, to like lots of data volume for communication and for storage, and basically having an app for everything. So that is today's world in IT. Now, if you go into OT, you may find devices like this one. And this is an actual device it's a Siemens control system, actually, that was built in 1971. So it took me a while to find something that's older than myself. And when this picture was taken in 2018, it was still in operation somewhere in Myanmar. And there's a very high chance that it's still in operation today. So basically a device that runs for 50 years. And of course, there's not an app for that. It doesn't have app for anything. The usability is, well, maybe good for the time, definitely not what they're used to today. And this is the kind of equipment that you may see in the field. And you may say, well, 50 years ago, that didn't speak TCP/IP and was not networked in any good sense, but it is controlling parts of a utility, and other parts of that utility are networked. So potentially, if an attacker gets into the utility as a whole, their action can influence also this device. So it becomes part of our security concern. So that's one of the challenges that I present today. You'll see I present a lot of challenge today and not so much solutions, because I want to show you that this is really a topic worthwhile exploring more for all of you, not just students, but of course, faculty as well. So one of the challenges is installed base. And this shows, the device shows that especially in energy, we have very conservative innovation cycles. So, cell phones, you get a new one every year, or every 2 years. Innovation cycles in energy are measured in decades. And generally, that's not a bad thing, right? Utilities being risk averse helps to keep the lights on, right? They're not too keen on trying out new things and failing because their customers don't like that. But we see from IT that there is so much more potential with the technology and the advancement that we have today. So that drives something that we typically refer to as IT-OT convergence, and which basically means that the value that we see coming from today's state of the art in IT technology pushes into the OT world. People say, well, you as an operator may say, well, if I can manage my whole finances from my phone, why can't I manage my substation from my phone? And there's nothing from a technology perspective that hinders us from that. So that creates a significant challenge and for cybersecurity to make sure that these two worlds don't clash but coexist. Another challenge is that whole topic of assurance. So as I mentioned before, typically what you do is you want to do vulnerability scanning, you want to do penetration testing, auditing, red teaming, all these nice things where you want to find out, are there vulnerabilities that I'm currently not aware of yet. And as I said, availability is king in OT environments. So whatever you do in terms of scanning, you must guarantee availability. You cannot do a vulnerability scan and have your systems crash. And that can happen because some of these devices are so old and they're still on the network, so it's a little bit newer than this one, that at least speak some dialect of the ISO model. But anyway, so some of them may actually crash if you do as much as a ping sweep. So you have to make sure that doesn't happen, and you have to guarantee that. Otherwise, you cannot do what you're used to in IT to assess these vulnerabilities. And you have to do them in flight, so doing operations, because if you shut it down, then you just don't get the same reactions and you don't get the same transparency. And another part of the challenge is whatever you do needs to be highly automated, because you have challenges coming from bandwidth, coming from scale, and coming from locations. Now, a typical example that I like to bring is if you want to do a pen test on an oil rig. If you want to go there in person, you probably have to go through 2 weeks of survival training just to be able to board the chopper. And that's typically no longer commercially viable. So if you want to do pen tests in specific environments where these devices live, you have to find better ways to do that. Automation, remote access, intelligence, anything. But the challenge is typically a lot higher than what you typically see in IT. The next topic, or the next challenge domain basically, is adapting to maintain a secure state. And in the end, it mostly boils down to patching. And we all know that patching is necessary. If you don't patch, then the bad guys will analyze your patches very quickly. And there's nice studies about how long it takes them to figure out how to develop a working exploit from published information about patches. So you need to patch and you need to update your configurations. There's really no way around it. Or the bad guys will take care of that for you and own your systems and operate them for you. And not in the intended way, of course. But again, patching must not create an availability risk. And an availability risk can be as much as a forced reboot. In IT, we're used to that fact. If our Windows system reboots after patching, that's perfectly fine for us. In energy, again, not so cool. In IT, we've come a long way, right? Patches these days don't really want a high chance anymore of breaking your system. But in the past, that still happened. And with all these different operating systems and these different configurations and these old systems in OT, that is still an issue there. So in order to address that, we need to figure out how can we increase patch quality and how can we increase resilience to bad patches. And then again, what's also necessary is good asset management and configuration management. And you would be surprised about how many industrial environments struggle with just the bare minimum of figuring out what they have in the network. So the asset management. But without knowing that, you don't know what kind of vulnerabilities you have and which systems are vulnerable and what your risk is and what you need to patch with which priority. And the last topic I want to focus on is monitoring and detection. And typically what you do in monitoring and detection, you have a security operations center, and simplified it a little bit, it boils down to these 6 steps that you see at the bottom. You have data sensors. You need to figure out how to get the data from your systems and collect them. And that can be as easy as using syslog or SNMP or just your PCAP data. But specifically in OT, and the older the devices get, for some of them it may be pretty difficult to actually figure out how to make them generate log data and how to collect them and how to basically bring them then to the next box, exfiltration point. Now, exfiltration means you need to get them out of your network. And hopefully you do it using something like a data diode here that makes sure that you don't create a new entry point and a new chance for attackers to get into your network by doing so. And then it basically ends up in your backend, in your SOC where you have your SIEM and stuff like that running. So typically the first thing you do is ingestion, and it typically involves things like getting the data into your database, typically in some form of normalized format. You do some data massaging, some normalization. Then you do some analysis, which is mostly like adding context, correlation, enriching data, all these kind of things. And your next step is where you need to find the needle in your haystack, right? You want to find out, okay, in all this data and all this log data that I gathered, where is an indication for an attack? And typically you use these 2 approaches. Threat intelligence, which is basically pattern matching. So you know the pattern of known bad things, and you just try to find the same patterns in your data. And if you find it, you kind of always know something fishy is going on. And you're doing analytics, which is mostly anomaly detection and specifically machine learning based anomaly detection. So you basically just want to figure out which one does not look like the others. And then you hope that this is an indication for an attack. And then once you've done that, you need to figure out how to properly respond. And I could talk about hours for each of this, but I don't have a couple of hours. So I decided to basically just talk about 2 of them in a little more detail. One of them is exfiltration, and help you to understand what the challenges are that we're facing there. So one thing that I said is typically you take all this data and you put it in a security operations center. And that makes a lot of sense because it really only makes sense from a scalability perspective if you have some form of centralized SOC. And it doesn't mean it has to be an external service provider, like service like Siemens provides, or what you put in a cloud. It can be an on-prem, SOC, which is basically part of your own company, but you can't have the complete analytics stack on each of your substations and in each of your sites. So you need to exfiltrate it. There's really no way around it. But here, one of the specific problems that you face comes from regulations, and I picked this out, and here's where we see NERC again, right? Because if you need your data, which is typically referred to as bulk energy system critical system data, it's a mouthful, but basically the critical data of your protected security environment. If you need to extract that, you need to make sure that you still comply to NERC, and that in practice isn't actually trivial. So two examples for that. So one is, well, using off-prem SOCs or even cloud-based SOCs is in principle permissible by NERC, but you're being audited frequently, right? And the auditing entities are typically the regional entities. I'm not going into detail who they are and how they work, but they typically come out to the utilities and audit them from time to time to see if they comply to NERC. And they have teeth. The fines can be pretty severe if you gravely violate NERC. The fines can be up to $1 million per day. So it is definitely something that utilities want to avoid. And as we heard before, they're risk averse, right? So if the rule isn't entirely clear and there's discretion for these auditors on whether or not using off-prem SOCs or cloud SOCs is permissible, this creates a risk for the utilities, because now it depends really on the individual auditor whether or not their setup will be found compliant or not compliant. So that creates a huge obstacle to utilities adopting new and better security features, and in this case, centralized SOCs, in order to better detect attacks on their data. And another challenge is here that this bulk energy system data must enjoy special protection, even if it leaves the protected perimeter. And this means things like, well, you have to avoid external routable connectivity and interactive remote access, things that we're very used to from an IT perspective, which all of a sudden makes it a lot harder to provide these services and these back-end services in a compliant way to utilities. And of course, these are just two examples from NERC, so very much focused here on North America, US and Canada. And we have a lot of people from all over the world here, right? And there's a lot of other regulations that apply if you want to create products for utilities on a global level. For example, the Chinese cybersecurity law, or the GDPR, the General Data Protection Regulation in the European Union. It's for a company like Siemens, it's almost infeasible to just have a separate device per country. So you need to figure out basically how to satisfy all of them. And in comparison to IT regulations and standards, OT is still a lot less uniform. And there's still a lot more work to be done to understand them and to understand what that means for your security features. So that's one set of challenges in exfiltration. And another one that's the last one I want to focus on today is in analytics. The first notion here is, well, data analytics requires data, right? And you may say, well, duh, of course, that's a no-brainer. But in practice, that actually turns out to be more complicated than you may imagine. And one of the big problems is that original malicious data is still rare. And don't get me wrong, from a society perspective, that's a great thing, right? It means that there are not so many, publicly known significant attacks on energy utilities globally, which is great because it means our lights are still on and don't go off, too often, at least not because of cyber attacks. So it's great news from a consumer perspective, but from a security analyst perspective, someone who wants to use data analytics, that is still that is a problem. Because in analytics, you have a lot of ways on how you use data analytics and AI. And if you in your current career haven't had a chance to learn about the basics of data analytics, please make sure you change that. It's really a must-have because this is a technology or a set of technologies that is immensely powerful and used to great extent and with great value. So make sure the basics are known. And I'm simplifying a little bit, but basically there are two main ways of how you do data analytics, supervised learning and unsupervised learning. So supervised learning is basically you have two buckets. One is known bad data. The other one is known good data. And you feed it to the algorithm and say, look, this is bad, this is good, this is bad, this is good. And then hope that in the end, the algorithm can differentiate if it sees a new thing and knows which bucket it is from. But for that, you need this labeled data, right? And if you don't have enough malicious data, then this is an approach that doesn't work well in practice. And for the same reason as before, genuine OT threat intelligence is pretty rare because there are not so many attacks yet. So if the supervised learning isn't the way to go, what about this other method, right? Unsupervised learning. And unsupervised learning is basically just anomaly detection. You just basically show the algorithm your normal operation and say, that's normal, that's my baseline. And now tell me whenever you see something that is sufficiently far away from that. So what is an anomaly? And then you say, well, hopefully that gives me some insight into this being an attack. And the problem with that, of course, is it typically generates a lot of false positives because something not being like the others doesn't automatically imply it's an attack. It may just be a benign outlier. But more on that later. But in practice, benign data is also rare. And it's not because it doesn't exist. Utilities have that data. But as we learned before in exfiltration, this data needs to enjoy special protection, and utilities are a little bit risk averse. So they're very cautious in sharing this data with researchers, for example, in academia. So in order to still be able to get that data, you need efficient, trusted, and effective anonymization, which is a whole set of problems on its own. Now, if that also doesn't work, then what are we left at? But fortunately, we're not out of options, right? The next best thing we can do is like, well, if we don't get genuine bad data and genuine good data, at least we can simulate our own data, right? And then train our algorithm with simulated data and hope that our simulation is good enough and that these trained algorithms can do their job. But the question is your generated data really relevant? And to tell you what I mean with that, I'm actually going to take you on a short excursus into this, which is, of course, theoretical computer science. And let me tell you a short story. So there is this famous problem called linear optimization. And in theoretical computer science, and I assume most of you know the background, but I'll repeat some of it anyway. Mostly concerned with how good or how quickly you can solve an algorithm if something is solvable at all. So for linear optimization, theoretical computer scientists showed that it is what they call NP-hard, which basically boils down to the fact that, well, if it's a general problem, cannot be solved in a reasonable amount of time if the inputs are large enough. So basically for standard inputs, we would not hope to be able to find an algorithm that can solve these problems in any of our lifetime. That's basically what NP-hard in the end boils down to. And there's always this funny joke, right? So there's this one guy and we forgot to told him that the problem is impossible to solve. So he just wrote an algorithm and solved it. So then for every input that he took, that algorithm solved an optimization problem. And of course, that didn't really sit right with the theoretical computer scientists. And they did not go gently into that good night and looked at that and found out, well, both are right. Because the funny thing about that problem is that in general, it isn't solvable in a reasonable time, assuming that P is not equal to NP. But the set of problems actually looks like this brush. So there are some instances of that problem that are hard, which are the spikes. And if you need to solve one of them, you can't, right? So every algorithm basically has this kind of spikes. So there are instances of that problem that are really, really hard to solve. But most instances are basically easy. They're like the base of the brush. And now if you take a practical problem, you basically take a random problem, it is like you're taking this needle and you're picking on the brush. And as you can imagine, your probability of actually hitting one of these spikes is really, 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 really low. So in practice, you would always hit the bottom. You would always be able, or the base, so you would always be able to solve the problem quickly. And that's an interesting problem, to me, an interesting illustration of that. because that basically takes us back to the question of, is your data relevant? If you simulate data, you have to make sure that this data really contains all these classes of your problem. Because if you forget the spikes and your algorithm isn't able to deal with the spikes, the bad guy only needs to find one of them, and they can get in and compromise your system without you being able to detect it. So even generating simulated data isn't a trivial problem. And the last part here is, as I mentioned before, well, anomaly detection is state of the art, right? That's what we're using these days, and we get awesome results with that everywhere across the industry. We still have false positives, and we need to deal with that, because in practice, if you have too many false positives, you create alert fatigue, right? If you have a whole SOC team of analysts, and all they do is chasing after false positives, and only once every couple of days they find an actual attack, they're just going to assume that whatever they are presented is a false positive, rightfully so, and it becomes too expensive and just impractical basically to pursue that. So it's important to bring down this false positive rate. And specifically in industrial security, that typically requires that you inject some domain expertise. And also that is a challenge. How do you do that in an efficient way? How do you capture the domain expertise? And how do you make it usable for data analytics so that it effectively reduces the false positive rate? Okay, so these are three classes of problems. And that basically already brings me to the end of my presentation today. So I hope that this has given you a little bit more insight into the issues that we deal with in industrial security, especially in energy, when we're trying to apply all the good concepts, and when we're trying to secure the energy grid, and the issues that are still out there, and where still more research is needed to keep the lights on. So I hope a lot of you found that interesting, and maybe consider a career in that area, because, well, I said, more research is still needed, not just, but also in academia, but also on our side in industrial research. And of course, shameless plug at the end, of course, we're hiring. So, feel free to visit our booth in the lobby, leave your resume, also visit the booths of the other sponsors and the other partners. Talent in cybersecurity is really needed by everyone. So, take that opportunity, talk to us. We're going to be there most of the time to answer your questions. Okay, thank you very much. And that's what I had for you today. So I think we have a little bit more time for questions. I'm ready for that.
Awesome. Yeah, thank you. Thank you so much, Dr. Otto. Yeah, we do. We have some questions that have come in, and I think what we'll do is maybe we'll just try to do those in chronological order. So the first one is with regard to patching. Which is more important regarding patching, keeping patches current or system availability?
Well, clearly system availability. Well, that's basically what every operator will tell you, because availability is one and only basic KPI that is really important for them, because that's the bottom line. That's what keeps everything going. So for them, availability is really the topmost thing that is important for them. Of course, that's not really comforting for us from a security perspective, right? Because we know, well, if we only patch like every half a year, there may be critical patches that can be remotely exploited that can bring the system down. So it can create a lot of risk. So in reality, everything that is of low risk will just be pushed to the next standard maintenance cycle. And it's a different story for everything that is considered a really high risk. And for that, it's typically a case-by-case decision. And utilities struggle with that because they need to understand what is really the risk. Is this patch, is this vulnerability so important that it's worthwhile powering down their power plant, for example, or their substation? And that's a problem for them to make that risk determination. But if you ask them, the answer will always be availability is more important.
Thank you. A follow-up, a second question with tag teaming, if it's okay, Stefan. This is from Dajer, referring to page 11 of your slide, but in general, I think you can figure this out. Wouldn't a distributed system be preferable due to the redundancy and backup that it offers? If one node is under attack, another node may take control. You don't even have to go to the slide. So
yeah, and I can quickly share back and go to that slide. Challenge of referring to. Not entirely sure where you refer to, but yes. So redundancy is is used to a great extent already in the energy grid, right? Because you don't just have attacks from cyber attacks from bad guys. You also have just standard equipment failure that can happen every time. So the grid is typically built pretty resilient. So, which I think is one of the reasons why we don't see a lot of widespread outages from attacks, because it's not for lack of trying. So yes, redundancy is a great thing. And I know there's a lot of research going on in like, well, if I have different nodes in the system, like different substations, and they can build like, kind of a peer-to-peer network, and they can monitor each other, can't we build a system that even locally without central control figure out if something is wrong and then take over operations from other parts of the network and make sure that failures in one part of the system or one node or a few nodes is basically contained and doesn't take too much away from, or doesn't create too much havoc on the entire system. So those are great ideas, right? And I've seen a lot of that coming out of academia. But as I said, bringing them into practice sometimes requires that the utility applies a complete new approach to their environment. And sometimes it may require them to whip out old devices and replace with new devices that are actually capable of doing that. And that creates a huge problem typically in practice if the new and better approaches turn out to be too expensive for an individual utility to actually shoulder them.
Thank you.
I think next in the chat, with regard to threats, and given the fact that we're in era industry 4.0, what threats, challenges can we expect in the framework of the data? I
think maybe reframing it, I think, is data going to be an issue, problematic attack vector is how I see that question being asked. Because yes, lots of data is being generated, there are lots of things being cyber enabled. How would you curate or manage the data, the security vulnerabilities that come through that pathway?
Yeah. So yes, it is an issue, right? And that's why we saw on this slide that, for example, NERCSIP requires data to be protected even if it leaves the direct electronic security parameter, because outside of it doesn't influence the control, but it's still considered critical data and still needs to be protected. So there is an appreciation that once you have collected data, then of course you need to protect it, because otherwise that may allow you to derive conclusions about possible attack vectors as well, right? If I use the data to find indications of attacks or indication of vulnerabilities, then of course the same could be done if the data gets disclosed by the bad guys to figure out what potential areas of attack are open for them. It's also interesting for them to understand how you analyze your data, because they may give them insights into what you see and what you don't see. And then of course there's this whole area which I also find really fascinating in analytics, which is basically adversarial analytics, to find out, well, can I craft data that fools my AI algorithms, right? And there have been great results showing like how you can manipulate, traffic signs so that your visual AI detector basically thinks it's a different sign. So of course that can also be theoretically done in attack detection, right? I can create data that maybe fools my SOC and my AI in the SOC to miscategorize an attack as a benign event or vice versa. So yeah, protecting the data and you misusing data, there's a lot of opportunity for that as well, and a lot of problems that are worthwhile doing more research on.
So one other question is, do false positives have a larger impact on OT systems than in IT systems?
I don't think so. Yeah. In the end, it's the same problem, right? If you have alerts, you have your automated way of dealing with them, and then in the end, you have your human operators that need to take a look. And if the amount of alerts are too high for the human operator, then it just means the costs are too high for you, or you create alert fatigue. And the same is true in IT and OT. So I don't think there is a significant difference. I think in IT, it's much more accepted that the cost for security are higher than in OT. So OT is still struggling. You still have in a lot of areas the OT guys and the IT guys not really seeing eye to eye. So your just your staff numbers, your capacity may typically be smaller in OT than in IT. So that creates an issue in practice, but not from the mere concept.
One other question, I think we still have a few minutes. So what are your recommendations for forming industry academic partnerships to solve industrial cyber physical security challenges? Would something like a demonstrative generic digital twin be viable as a reference platform for trying some of these ideas rather than trying them on real systems, as we all know is going to be much more of a disaster when you do it in the OT context, right? Or will the data always be too sensitive to share? So even ignoring the data, there is other issues. So I will let Dr. Otto respond to this.
Yeah, thanks for the question. And it's something that we're pursuing, right? As an industry, we are fully aware that we don't know everything, right? So we want to work with academia because of the vast number of great minds that work there, both in faculty as well as all the students. So all the ideas that come out of it is that we appreciate that left side of that valley of death, because that's where we find the ideas that we can hopefully take into commercialization and of course ideally together. So yes, these kind of partnerships are immensely valuable for us. The question is how can we make them work better, right? How can we make sure that the outcome in the end is more of basically of the ideas which actually make it in commercialization, and setting something up like a test bed that allows us to quickly test ideas and showcase their merit, or evaluate commercial feasibility or viability. I think is a great approach. And we operate test beds ourselves. We know a lot of universities operate these test beds, so that's really great. The data part is really the limiting factor, but I think it can be overcome, right? And you can work with data owners. You have to make sure that data owners trust you, that they remain in full control over what happens with their data. If they are convinced that the data is only used for what they approve, they will be much more willing to give access to the data. And even if that doesn't work, you can set up environments that allow basically to work in a, how should I call it, disconnected fashion, right? You set up your test bed, and then you put in the data, and then you delete the data again. And in the meantime, no one has access to the data who wasn't approved by the data owner. So you can still generate results, you can still generate the insights and validate your approaches, but you don't need direct access to the data. Sometimes maybe it makes sense to have these labs and put it into the environments of data owners. It's actually something that we're doing ourselves, that we built a little bit of a mobile lab. We said if the data doesn't come to us, then maybe we go to the data. And then maybe we can do these kind of testing in environments where the data owner feels comfortable about us doing that. And I think there's a lot of opportunity to explore that more. And I think, just because industry is rather small and academia is pretty broad in terms of all the ideas, working together has always been a recipe for success for us. So that clearly makes a lot of sense.
Thank you. One more question. Is red teaming considered not as useful as a systematic purple team-like approach in terms of identifying vulnerabilities?
I wouldn't say so. I mean, to me, so red teaming, it depends always a little bit on how you define them, right? To me, red teaming is basically the lowest level is vulnerability scanning, just tool-based, and you have penetration testing where you go after a specific target. For me, red teaming is basically just you want to get into, you want to achieve a mission, you want to get access to some data, but you're no longer limited to a specific application, trying out everything. And the purple testing takes into account the blue team. And you don't just want to try out how you get into something, but also how well it can get detected and how well the defenders can react to that. And ideally, I think a purple team would encompass what you would do in a red team testing. And if that's how you do it, then, well, I think it's a no-brainer to say the purple testing is probably more valuable, but it's also more expensive because you have to bring these both teams in, and you have this close interaction. And in this case, the utility would have to have a blue team where testing it really makes sense, right? Not everyone is mature enough. So typically you start with the lower levels, and you start with a red team to just show the risk that someone faces and use it as a motivation to increase the maturity of the defenders. And then once you have that, then this, basically cat and mouse game of a blue team exercise, of a purple team exercise makes a lot more sense.
Thank you. I think we're at 12:57, 12:58. In fact, so I have a couple of questions, but one thing a shout out is for those of you who are looking for jobs and so on, or careers, internships, to figure out if this is the right thing. You should try internships, be it in Siemens, as Dr. Otto rightly pointed out. Others also are useful, but go reach out to them, talk to them, and send your CVs and so on.
And I'm going to be in the booth in about 10 minutes. So if you have more questions regarding the presentation, that's where you find me.
Yeah. So thank you, Steph. Thanks, Dr. Otto, for this talk, and thank you all for your questions. And that was quite interactive and insightful. For those of you who could not participate, we'll have these recordings, so we put it on. And
we'll get those online. So thank you so much for everyone for attending our welcome address and for the keynote. We look forward to seeing you on the platform. Thank you so much.